So thanks again for joining. Today, we're going to talk about not just naive GLM. This is the observation. Here's how I fit a model to it. But we're trying to understand what kind of behavior complexities are going to come into the picture that might bias our results in different ways. So what we are observing is not going to be the same as what we are really interested in, and that's called detectability. So we are going to talk about detectability, what that is, how to account for that to some extent, and this is going to continue on day 3. So we'll have breaks, but feel free to stand up and grab a drink in the meantime. So if you download everything, then you should be able to, maybe I'll just do it. Stop. So now if I go here, here's day 2, I can unzip, find that folder, and inside that folder, I created this docs folder for that HTML version. And here is where you can find the slides that I'm also going to show you. So we begin with a bit of introduction again, slides, me talking, and then before the break, we are going to jump into some fun simulation programming so that we get familiar with the tool that we are going to use moving forwards. So we covered how to deal with data wrangling, did some regression, and now on day 2, behavior and removal models and assumptions. As I showed to you, if you go to the releases page, you can download the zip, unzip, double click on the workshop file to open it up in RStudio, and then you can create your local copies if that's something you'd like to do. This is how you create your local copies. You source the functions file and then say QPAD _local day 2. This is going to create copies of the day 2 markdown files. So your changes won't get lost or overridden by Git if you're using Git. Otherwise, just every day you might get a different folder. And once we are done, you can just copy your files together into one place, and then that way you'll have it saved. And also, initially you installed a bunch of packages, but as I was preparing for today, I fixed a couple of things and added some options to this bsims package. So if you could run this line, remotes install GitHub psalemos/bsims with capital first S, that would be great, because otherwise you might see some unexpected errors as we are going to use this package later. So we're going to talk about detectability, and in a very plain term, what that means is the probability of a species detected given that it is present at a station where you go and sample. And in this little notation, capital N stands for the true abundance, what is within your area that you're sampling. Say the true abundance is 3. What we look for here is whether that number is greater than 0 or not. And when it is 0, there is nothing to detect. When it's greater than 0, you can detect 1, 2, 3 individuals out of the 3, n equals 3. And so y, that is your observed data. This becomes anything between 0 and 3, because even though there is 3 individuals present, you might get really unlucky and detect none, or you might just hear 1, hear 2, or all 3. So y, if n is greater than 0, can be also greater than 0, in which case we detect that species. And this notation means probability of y greater than 0 given that n is greater than 0. And this pipe here in the middle indicates that this observation is conditional on this true state. So this is a notation that we will use for conditional probability, given that there is anything present, do we detect something greater than 0. Now, in an occupancy framework, when we are really just concerned about whether we detect 0 or not 0, or whether there is 0 or non-zero true number of individuals, we can talk about different outcomes. And by different outcomes, I mean what we observe. So there are true positives, which means the species is there and we happen to detect it. So our y, the true observation, is going to become greater than 0. And in occupancy, we just think in terms of zeros and ones. And 1 means that the abundance is greater than 0. So I'm trying to always talk about abundance here, but now in an occupancy framework. And I'm not going to go into the details. This is more just for you to look up all these probabilities if you want to. But then this involves these two components, and phi means that is the true probability that the species is there. That's the occupancy rate that we are interested in. And delta is the detection probability. So the probability of observing a 1 is going to be delta times phi. And then we also talk about non-detections when we, a 0, observing a 0, which comes together as false negatives and true negatives. And true negative is when the species is not there, there is nothing to observe. And then the false negative is when it is there, but we happen to not observe it. And so this probability becomes 1 minus delta times phi. So these are often called marginal probabilities, and these two add up to 1. So obviously we can only observe a 0 or a 1. So these two probabilities need to sum to 1. And this is used in occupancy modeling to describe the likelihood, which is then maximized. And that's how we estimate these parameters, or like those betas, if these depend on some covariates. So I talked about this is to kind of bring in this notation of the true state and that latent variable that we can't directly observe, and this delta, which is modifying that before we detect anything. So as a result, we get a 1 less often than the true probability of occupancy. As a side note, we estimate this delta, and we can also then get this probability of observing a 0 when the true abundance is really not 0. And this is really trivial to calculate. But what people often ask is, what is the probability that the true abundance is not 0, given that we observed a 0? And this is a different quantity. So you can see here, the conditionals are switched. Y equals 0 given n is greater than 0 versus n is greater than 0 given that y equals 0. And if you do the math, then you can see that these two probabilities are not the same. So it really depends on what you are asking. And this is easy. This is a bit more difficult to calculate because this requires you to know the true occupancy as well, or at least have an idea about what that might be. Otherwise, it's really hard to answer this question. And just from experience, people often forget that this is required. So this is nothing to worry about for our QPAD workshop. This is more just in the notes, so you can look it up if you're ever interested in asking this question. For example, how often should I go back? When should I stop looking for a species when I keep not detecting it? So now let's talk about abundance. Our notation already brought it up that really what we are looking for is true abundance is 0, 1, 2, 3, 4, 5, 6, or 200. As we saw one case, Canada goose 200 count was in our data. So this is the true number that we are looking for, and we can detect anything up to that number. So if our true abundance is 2, then we can detect 0, 1, or 2. If it's 0, then we can only detect 0 out of those ones. So now, if you think back, this calculation looked intimidating to some extent, I guess. I made it that way. So now you think about all these possible combinations and how to write that down. This becomes even more challenging because then you need to think about all these combinations. So we need some smarter way, and there are multiple methods out there to deal with that. But all of those require ancillary information. And by that, I mean not just the count, not just Y itself, but also maybe you repeat your visits multiple times. So you get different Ys and you assume N is still the same. And then you can deduce something about this delta so that you can estimate your true interest, which is N. Or you have the counts coming from different distance bands, the amount of individuals detected at different distances from the observer, or multiple time intervals, which we are going to talk a lot about today, like first minute, second minute, third minute, which individual was first detected in which interval, where you have multiple observers at the same time repeating the counts. Or if you have none of these, you still need some kind of assumptions, more assumptions than if you have other extra information. And these assumptions are just going to help you identify these quantities without any kind of replication. We are not going to talk about single visit approaches today, but that's what I mean, either for occupancy or and mixture modeling. You need to make some assumptions, and that if that is satisfied, then you can estimate this quantity without any kind of ancillary information. And also often you need larger sample sizes. Somewhat related to the single visit methods is what I call the myth of constant detectability. When you have multiple visit occupancy and N mixture models, you can estimate a constant abundance or constant occupancy because you just have more replicates, but it also comes with some assumptions that people don't always like or which are not often satisfied in practice. And so these methods, because they can estimate a constant delta, these are often seen as superior to those techniques where you cannot estimate this. And so this is just a little blurb on what that means really when delta is constant. It means you're in the same region, in a similar habitat, in the same year, on the same day, at the same time, by the same observer, using the same protocol. This is what leads to a constant delta. If this is all satisfied, then there is merit in making this as a requirement for a method to work. Otherwise, if you are spreading your effort across multiple regions or happen to visit different habitats over multiple days throughout the season, then you might see that delta varies, and as a result, you might need methods that can deal with that variability. So this constant criteria becomes almost irrelevant. And when you look at the data, and it's not just my thought on this topic, but when you look at how many times the null model was best supported, out of 75 people in one study we found it was 15. Then later on a slightly bigger data set just for removal modeling, we had 147 species. Out of those, the constant model was best for one species. So it often comes down to sample size. If you have low sample size, you can't really fit anything else than a constant model. And in this case, knowing that constant delta is still the best you can do. Just to give you an idea how components of delta can vary, for example, with time of year, you see that early in the season it is usually higher, and later in the season it drops down. So this is singing rate per minute over days in the breeding period in Canada. And then also with time since sunrise, how it's changing for different species. So this doesn't indicate that there's a constant delta involved. And then you can also kind of look at these spaghetti graphs and just create a different kind of visual for all kinds of models, showing you the same pattern, that there is a decrease over time with these availability probabilities, which we're going to estimate today. The kinds of biological mechanisms that we need to think about is migrants are arriving to the breeding grounds, and their phenology is driving these changes with, for example, day of the year. Early in the season, they are looking for pairs. Later, it becomes less of an issue to vocalize that much. Or your study spans across biomes and time since local spring, or even sunrise times are going to be different. So you can kind of look at all those variables and how when they arrive back to the breeding grounds is related to the first day of spring, things like that. And then also time of day or time since local sunrise, if you're looking at over larger areas, that is going to be important because early in the morning, they're more active. But some species, that's the opposite. So it really comes down to what species you're looking at and how their daily and yearly activity patterns change. Now, when we talk about perceptibility, and I'm running ahead a bit, so once they are present, then they need to behave in a way so that we can detect them, they move around, sing. And once that happens, then there's the perceptibility, whether the observer is able to detect them or not, as a function of how far they are from the observer. And that is also modified by, for example, tree cover or land cover types. This is dense conifer, dense deciduous, sparse conifers, sparse deciduous, and open habitat. You can see across these habitat types, there's a certain pattern, what the probability of perceptibility follows. If there is more tree cover, this probability drops down. Same goes in dense forests. So this is just to give you an idea about how these vary and what kind of biological mechanisms come into play, which is what we are going to look at either as covariates or as things that influence detectability. So some physical mechanisms why sound coming from farther away is less detectable, because trees block the transmission of the sound. Broadleaves rustle more, so there's more background noise, which makes it harder to identify individuals. Loud sounds travel farther, low frequency sounds the same. So there is going to be a difference not just across habitats, but also across species. When they arrive to the breeding ground, how large they are, and as a result, what frequency their sounds have. So we have these conditional steps involved. If there are multiple individuals present, which means n is greater than 0, then we need some kind of signal to be able to detect them. We can either hear or just through looking at them, they move around, and as a result, we spot them. They make themselves available for us to sample. And then once this signal is given, then that needs to be received by a sensor, which can be a microphone or our ears or eyes. And this is the two quantities we are going to call P and Q. And so when we look at these quantities also imply a predefined total time duration and the maximum counting duration. Because when you look at P, if we listen longer, then we might detect more. Am I still here? Okay, because Zoom just told me that I got signed out. Maybe that was Kim leaving. Okay. So when we look at P, that means the longer we stay there and do the survey, the more chances we have to hear and see the individuals. And Q implies that the larger area we are sampling, the more individuals we might encounter. So now back to QPAD. We had this equation on Tuesday at the very end. So we observe our counts, and then that is a result of the true abundance and some unknown. And so the true abundance can be also written as density times area multiplied by the availability and perceptibility. And if you kind of rearrange this a bit, then you can read it as QPAD. So we have population density, the area sampled, probability of availability given that the individuals are present, and then probability of perceptibility given that they are present and they are available. So we can use multiple time intervals and distance bands to estimate these quantities. And why that's the case is because as the sampling duration increases, this probability is increasing too. And as we increase our sampling area, so the distances, then we see this other, the perception probability to drop down. So these are monotonic functions of time and distance. And as a result, we can build quite simple models to estimate these quantities. So if we have the total counts broken down into some sub-intervals, either by time or by distance, then we can do a lot more, as opposed to when we only have the total count of Y.
Peter?
Yes?
There's a question from someone that is thinking beyond birds and thinking on other cues that your target species could leave, like scats, footprints, or whatever. Mm-hmm. So maybe if this is not jumping ahead, maybe you can, at the point where you see this could be applicable to other taxa, maybe
sure.
The connections, yes. Or at this point, or when you see fit that, yeah, it's interesting that this could be also applied not only for birds, but people may want to know when does it apply or what caveats could be
right
for other taxa.
So from the simulations, it's going to be a bit more clear what kind of situations we often discuss when we talk about point counts, but just from the perspective of movement, I think availability becomes less of a quantity that you can well quantify, but still if you're using camera traps, then distance sampling principles would still apply, kind of how far you see an animal in front of the camera in that view, and whether you see it within a certain distance or farther away, that is important information that people use when analyzing camera kind of data. If you are looking at amphibians, then often you don't really have distance information, but you have a lot more information about their vocalization activity over time. And that's something you can more easily analyze. And so regarding the movement patterns, most of the thinking I've done over the past years regards land birds and territorial songbirds. That means that their movement is more confined and they often try to repel each other from each other's territories. And as a result, and also their home ranges or territory sizes are often comparable to the area we are sampling. And what happens when you have large moving like mammals or raptors, owls, is that the area we are sampling is much smaller compared to their large home ranges. And these home ranges also happen to overlap, right? So there can be multiple coyotes or owls using the same area that we are sampling. And this point in space is just becoming really small compared to their home range. And that is a special kind of problem. And you can think about that beyond being present and being available, being detected, you also need to be using that area at that time. So almost like presence is given because these animals can move 500 kilometers. So you can't say at every minute where they are unless you have like radio colors or something on them. But that's a different kind of data. This is like when you don't have this kind of tracking, but you can still talk about what is that probability that your sampling area is going to be used if you know their use patterns. So that's what I would add. Again, extra information is required because there's another unknown coming into the picture. Hope this answered that. And we are going to look into movement. And through that simulation, you can make movement really large, like lots of overlap across the territories, and see how that might affect the results using these methods that we are going to discuss. So we'll come to that to some extent, but we are not going to fully resolve that for non-territorial animals where you have this overlap and the sampling area is much, much smaller than their home range size. So now if we want to think about how we can generate the data under these ideas or models or probabilities, then this is what we would do. In R, we would define, we have density, 2 individuals per hectare, an area that we are sampling 1 hectare, and we have P and Q set to 0.8, 0.5. These are these probabilities that when individuals are present, how often they are going to be available, and then once they are available, how often they are going to be detected. We can set our sample size to 100, nice round number, and then say N, which is the true abundance, follows a Poisson distribution. R means give me random numbers from a Poisson distribution. This is going to be a vector of length N, and lambda, which is the mean of the Poisson, is A times D. Area times density, which is 1 times 2. And now what we observe is Y. That's coming from a binomial distribution with size N. So if at location 1, N was 2, then with this probability, we are going to get a 0, a 1, or a 2. So if this probability is high, we are more likely to get something a 1 or a 2. If this probability, P times Q, is low, then we are more likely to observe a 0 or maybe a 1. So now we run this simple random number, few lines, And this is what we get, similar to that table that we saw before. The true values versus our observations. When the true value was 0, we observed 0. When it was 1, sometimes we observed 0, sometimes we observed 1, and so on. So this is what we would get from a simulation. And if we have a model that describes this, this Poisson / binomial model, which is like a multiple visit and mixture type model, if you can think about it that way, and you know how to estimate this lambda and this p, then you are done, right? This is going to give us a way of estimating these quantities, and we would know if A is known, then we can estimate D. So that's how we would approach this. However, this model looks really simple. So this is what the math notation would look like. N follows Poisson with mean D and A, and Y is binomial with size N, probability P times Q. But there's a lot more detail. So if you imagine this N is being number of birds, birds are a lot more complex than just multiplying together two numbers. So there are all kinds of assumptions that come into play. For example, those N observations are independent. When we look at Y, that involves no double counting or no undercounting as well. We know the area, and that area over which we count the individuals, the distance is measured without error. Our detectability is independent of the abundance. So if there is more individuals and they have to vocalize more to just signal their territory, then maybe there's a relationship between P and N. But this model assumes there is no such thing. There's a lot more, but this is just a few that we can quickly see that might not be always the case. And another reason why we need a simulation method that is different than just saying, give me random numbers, is if I do that random number thing and repeat it many times, create some data set, fit a model to it, then I'm going to find either the model is not working, so there is no point in publishing a paper about it, or the model is working, and that means I'm going to get an estimate of P times Q and D. That's all good. But how do I make sure that all those assumptions that go into the model that I created are actually realistic? So how to make sure that that model is really capturing my system out there? So if you think about classic example in textbooks, you talk about a coin toss, right? When you introduce the simplest distribution of all, binomial 0 or 1 with probability P, you make a coin toss, is it head or tail? But if you do that in real life, it is not just head or tail, it is how high it goes, how much it spins, what is the weight of the coin, and so on. Now think about birds. Birds are a lot more complex than a coin toss. They move around, they have wings, they have brains, they vocalize, they socialize. So how do we capture that? I've yet to see any problem, however complicated, which when you looked at it the right way, didn't become still more complicated. So this is how I feel oftentimes when I work on this little simulation package, that I could introduce so much more. So it's more about, where do I stop? Obviously, I need to sleep sometimes, so that's where I stop, but still, things are bugging me. Oh, I should introduce this or add something more. And also, simulation things are becoming more popular. And this is the great thing about 2020 in the pandemic, that at least me, I could listen to pop music again. There were so many great albums coming out that wasn't the case in previous years. Love the simulation we are dreaming in. So about the history of this simulation package that we are going to use, which is called bsims. And if you played with video games in the 90s, then you might recall a game called Sims, where you had to like manage people who live their lives. And this is how I feel about this bird simulator, that we manage a population of birds, how they behave and how we observe them. In the past, I couldn't find a lot of things like this. Either it was movement trajectories to mitigate mortality near airports and wind farms, or Beth Rigby had a PhD thesis in 2016 simulating the effects. It comes with a bunch of R code that's slightly different from what I had in mind. So I wrote my own. So my goals were that I wanted to test statistical assumptions using a bit more complex simulation than just playing with random numbers. And it is also helpful to aid survey design. If you have an idea about how the system behaves, what is the best method to capture that? How long, how often, how far you should count birds. And also I wanted to make it enjoyable. So it's not just, oh, let's do some R coding, but it's actually interactive. So you're going to see shiny apps. The design is, we're going to simulate small landscapes. So it's not going to be a full survey. Just at one point, what happens with the birds and what happens when we put an observer in the middle. And I was trying to capture the most important mechanisms and also make it efficient so that within like an hour, we can steal some results and we won't have to wait for days. And it's also easy to extend, to write your own function or modify the outputs so that you can incorporate other complexities that I decided not to. And as it's the trend now, if you write an R package, it comes with some prepended words like bsims. If you start typing this in RStudio, then it is going to offer you functions beginning with that name. So if you start typing bsims, it is going to list all of these in the autofill, and then you can pick the right verb. You can initialize the landscape. That is just a habitat, no birds, no observer. Then you can put birds in it, how many, where exactly their nest locations are. Then you bring them alive. They are going to move and vocalize. And then once this reality is in place, then you put a detector or an observer in the middle to detect some aspect of their behavior. So this is the physical side of observation. And then the human aspect of the observation process, how you perceive the distance, whether there is any error involved in that. Can you identify the individuals or you are mixing them up? These sorts of aspect of it is in a separate layer called transcribe. So you initialize, populate, animate, detect, and then transcribe. So these are going to be the layers for these simulations at one spot. And now, just to get the math out of the way, I'm going to talk about the behavior events. So if you start surveying now and you have a stopwatch, then you can count when a certain event occurs, whether that's a movement related or a vocalization related event, and you register this time. And then you can talk about this density function, which is going to describe the distribution of times to these events. And then once you have this exponential distribution with a certain mean and variance, then you can also think about the cumulative distribution function, which is something we are going to use quite a bit today. So this is the piece I'd like you to concentrate on. 1 minus e to the power minus t times phi. And phi is the rate at which these events occur. You can see now I already made a link to this quantity p, because this is how we are going to estimate probability of availability. But with this math, I'm just trying to make the connection with something called survival modeling. So we look at this cumulative density function, which is also called the survival function. And then based on that, we can define the hazard and the cumulative hazard, which is more in the survival modeling literature, what people often talk about. We are going to concentrate mostly on the CDF and see how that looks when we actually plot it from the data or different kinds of data sets where we can run into this. And one other interesting thing to note here is that if you recall, the probability of a non-zero count under the Poisson distribution, that's the same as this, because there's a relationship between exponential and Poisson. So we are going to use this exponential model, and you can think about this, that events happening are independent of each other. So this is the most simplest way of thinking about events happening over time, is that one event is not going to increase or decrease the chances of another event. So it is also called memoryless or homogeneous Poisson process when there's a constant rate. It becomes non-homogeneous when this rate is changing, for example, as a function of time of day, time of year, and we are going to see how to estimate those effects as well. So this is one of my last slides here. Over time, we start detecting individuals, and each line is an individual. We have 52 here, as I remember, and the first detection is marked with the filled dots. All the subsequent events for each individual, those are just the empty circles. And if you put together the times to first detection and get this rugged line, that is approximated with this cumulative function that we talked about, this 1 minus e to the power minus time times rate. So this is the red line. And now you can see how these events, and even the binned version of these events, how many events happened in the first 2 minutes, the next 2 minutes, and so on, are going to be helpful to capture this shape. And if we know this shape, then we will know what the maximum was, right? We are going to see where that is flattening out. So if we don't observe everything, like we just do 1 minute, still we get an idea about the shape and how far it is going to go. So we can take this probabilistic thinking and use it back to estimate this abundance, which is 52. So here, this p is multiplied by n to get this number. So this is my quick introduction. And we are going to ignore perceptibility for today. So Q is going to be 1, but P is going to be something between 0 and 1.